Hi, I'm Paige Roberts, and I'm here at DataCon LA to talk to you about how the evolution of data architectures is bringing business intelligence and data science closer together, how they're unifying analytics. Now, I strongly believe that the technical and spiritual unification of business intelligence and data science can make a powerful difference in the impact of data analytics on a business overall. So I'm going to share my screen. There we go. So you should be able to see my slides. There we go. All right. So let's launch in here. So first of all, I want to talk to you about the fact that predictive analytics and data science is not something that's coming in the future. It's something that we deal with every day. People are doing data science to do analytics for cybersecurity. They're doing predictive maintenance in factories. They're doing operations optimization. We're doing software optimization. We're doing everything from smart agriculture to increase crop yields for farmers to geospatial analytics so that Uber can get you a car in under 7 minutes. This is part of our everyday lives, and it is touching every aspect of our lives. But the thing about these people who are all doing this advanced cutting edge data science, they're also doing business intelligence, and their companies depend on the same analytics that they've had for years to continue to run well as the cutting edge new analytics that are making a difference in all these different industries. So I want to kind of set the Wayback Machine and let's look at a data warehouse architecture from many years ago. So I've been in the data management business for about 23 years, and this architecture predates me. So it's been around a while. And the thing about the data warehouse architecture is it's been around a while for some good reasons. It's very strong architecture. It has some things that every company needs to function well. So let's look at this architecture. The first thing that you see is that it takes a lot of different data sources and essentially de-silos them. So it takes all your transactional operational systems and moves them. Now, the thing about this is each one of those operational systems a lot of times is itself a database. It could do analytics right there in place. You could do customer analytics right on your CRM. You could do financial analytics right in your ERP system. It's like there's no reason why you couldn't. The problem with that is they tend to be not very quick. The response time is not great, but that's not really why we started doing data warehousing. There were two primary reasons. One is that, yes, you could do analytics on one system, but you would only get one tiny piece of the picture. In order to get the full picture of your business, you need to get all of the data sources and look at all of them when you do your analytics. Now, the other aspect is that these are operational systems that the company runs on. So the last thing you want is for an important transactional system that's key to your business to be bogged down by an ad hoc analytics query that hogs all the resources. So you want a database that's completely dedicated to nothing but analytics so that you can use it for analytics and not mess up its other purpose, because that is its purpose. So a lot of databases were built for nothing but analytics, and they were optimized and created in different ways. So they became far smarter at this kind of querying and this kind of data processing, and that made them powerful. Plus you had all this ETL. Now the ETL meant, you extracted data from all of these sources, you combined them and transformed them and cleaned them up and generally made sure they were accurate, there weren't duplicates, there was, this was all good, solid, dependable data before you put it in your analytics database, because nobody wants to do analytics on inaccurate data or data that's duplicated or, whatever. You want good, clean, solid data to do your analytics on. So that's great, but that ETL part of the system was demanding, and it demanded that somebody, define, which columns are we going to pull from the source systems, and how is that going to look in this target system so that it's good for analytics, and what do we leave out? That was important because you couldn't take everything from all of these different systems and put it in your analytics database, because those things were expensive. And a lot of times, and they lived on hardware that was expensive. In fact, a lot of times the hardware and the software came together as a thing. So you would buy an appliance and it had the analytics database built in, and you fed everything into it, and you did analytics on it with SQL. Or with possibly you had some visualization software, something like Looker or Power BI or Click or Tableau or something along those lines. And that sent SQL into the system, and that did, the same thing. That's where your analytics were. Now, it didn't scale well. So if I wanted to get a bigger system, sure, I could do that, and it would process more data, but it would not be cheap. And chances are I would probably want to go and buy a system that was way bigger than I really needed, because as my data scaled up, I could only scale within that one machine. And when I started hitting my limits, I had to go buy another machine. So it was very limited in certain ways, but it did have some incredible strengths. So the strengths of it were that it was ideal for reporting, for business intelligence, for a lot of the things that companies depend on these days. So they went basically with this architecture from doing business with guesswork to a large extent to actually looking at data and knowing how your business was doing, how it had done in the past, what sort of trends to expect. Things like, every spring I have this bump in demand, so I better make sure my supply can meet it. Every Christmas I have a huge peak in sales. I got to make sure I can deliver. That kind of thing. It's like, this is all stuff that you could see by looking backwards, and that's pretty neat. And it was very performant. You definitely didn't have any trouble with performance with these things. They were optimized and like race cars. They were really fast, very performant. You could get back your answers as quickly as possible. And the extra cool thing about this was concurrency, which meant not just I or me in a small team, but if I have 1,000 people in my company, 1,000 people could use data to get the answers that they needed. Now, obviously, 1,000 people probably couldn't write SQL queries, but that's why you have business intelligence visualization tools, because they're easy. You can look at them and you can go, oh, well, I want to know more about that. Point at it, click, and it generates the complicated SQL to go back and do the analytics to display the new information for you. So it democratized data-driven businesses. It made it possible for everybody in the company to use data to do their jobs. It was also, because it's been around so long, it's a very reliable technology. It's very secure. You didn't have to worry about where your data came from because it was pretty well documented. There was not a lot of confusion about lineage, provenance, things like that. It was just really powerful for doing this kind of analytics. Now, of course, it had some strengths. It was expensive to scale. It only did structured data, rows and columns only. That's all it could handle. The ETL tended to be a little slow. So maybe, if you did ETL every 3 hours or once a day or whatever, all that great performance, would tell you really quickly what happened yesterday. It frequently was working on data that was a little old. it was only good for business intelligence. Where the new kinds of things that where you're trying to do sophisticated analytics on, using machine learning, or you're using, I don't know, you're using neural nets or whatever. It's like if you're trying to do something really powerful with it, it just wasn't designed for that. And it couldn't handle streaming data. So even though it had this fast response, you couldn't feed data into it rapidly and respond rapidly, which is something that that the streaming business use cases and IoT and things like that really required. So we came up with this new idea. Let's have a data lake. Okay. Now the idea behind the data lake is I can pull in data from a bunch of different sources. It doesn't have to be just structured. I can have semi-structured, I can have hierarchical, and I can stream them in as fast as I want to. Zoom, zoom, keep loading data all day long, fast as you want to, big pipes, goes in there, and now I have my raw data. And it can scale as big as I need it to. So we don't have that scaling problem anymore. It's great. It's affordable. If I want more storage, I just add a few extra cheap computers. It doesn't matter if I'm going to reach capacity in a year, because then I can just add a few more cheap computers and keep growing that way. And that works great. Now, the cloud made it even easier, of course, because then you can put all that raw data into a cloud storage format, and you don't even have to manage the cheap servers. Somebody else does that. It's cloud. It's somebody else's data center. They can worry about that. You don't have to worry about that. And you have that nice scaling, and that's great. And cloud storage is pretty cheap. Now, this raw data, of course, isn't necessarily great for business intelligence. It can be used for machine learning and stuff. Sometimes you want to start with that raw data for exploration and experimentation and stuff. But even for data science, you really need to do some preparation on that data. It's got to be combined and cleaned up and transformed, and this is starting to sound kind of familiar, isn't it? So data prep and ETL are really not that different, but the end goal was a little bit different in that I want to be able to do data science on the data when I'm done. I want to do machine learning. I want to things. So maybe my granularity was a little lower. And most of all, I didn't know what to leave out, because what I leave out for this this particular analysis might be different from what I leave out for another one. So schema on read was a pretty cool idea in that I could put the data in, and then I could decide afterwards which pieces of the data were important for what I was doing. And then later I could ask a different question and go back and get a different set of data. And I can even do it as I was asking the question. So that was pretty neat. So there's a lot to recommend the data lake concept. Now, it did do a lot of that ETL, only now we call it data prep, but same idea. So we refined the data into a format that was still scalable, but much more efficient and much more easily queried, more queryable. So we found out we still need business intelligence. So we stick a query engine on top of that, and we're like, okay, it's sort of like an analytical database, kind of. And it has some of the functionality, but I can also do my machine learning. I can use my Jupyter notebook. I can use my Python. I can use my R, and it's like, well, sort of, because R and Python and all those, they're not that scalable. They're not really meant for a petabyte of data. If you have hundreds of terabytes of data sitting in your data lake, your R is not designed to handle that. So, well, if I want to do data science, that means I got to extract some samples from the data lake, and I got to go somewhere else and actually do my data science and train my model and all that. Then I got to bring it back, and somebody's got to rebuild it in some other format, maybe Spark. I could do my work in Spark to begin with, but trying to do all that experimentation and stuff is not so easy in Spark. Python and R are much easier to use. Jupyter is way easier to use. Even SQL is easier to use. So this was kind of some strengths, certainly, It was much better for machine learning and data science than the old system. Unlimited scale at affordable unlimited scale. Streaming data, not a problem. Semi-structured data, JSON, Avro, all these unusual formats. Even, CSV has been around forever, but this made it easier to handle. Complex data types. So we came up with some new data types that were cool, like ORC and Parquet, that could store hierarchical data in highly efficient formats. So that we could store a lot. So we can store years worth of historical data and see patterns and learn. And it was pretty awesome. And we had schema on read, that ability to apply structure at the time that we are asking the question, as opposed to trying to figure out what structure we're going to need in the future. And, sometimes you guess right and sometimes you don't. But it had some weaknesses. One of them is kind of surprising. The performance is just not very good. I mean, this is something that's designed to process large amounts of data. We really thought on a data lake we'd get great performance, but we don't. The database is much better at performance, and it doesn't do concurrency. So if I have a small data science team, 5-6 people, data lake is awesome. But if I want to then take that machine learning and analytics and make it available to 1,000 people in my company, no, that doesn't really work. No, data lake's not designed for that. It's very complex. Even if I'm putting it on a cloud, it's still going to be a little more complex to build and maintain and keep track of than a simple database. So that's a little bit of a problem. And it's immature tech. It's just, it hasn't been around for more than 10 years. So it hasn't had a chance to get that level of security and governance and a lot of other, masking and privacy and all of that stuff that we kind of require from our data processing now. Okay. So then what happened? Well, people figured out that the data lake by itself was not good enough. But the data warehouse by itself was not good enough either. So what happened is they have both evolved over time to become more like each other. And also, people who are using it have realized that I need the strengths of both. I need both of these things to really work, to do my business. My business needs business intelligence and it needs data science. And this is maybe the best way to do data science, and this is maybe the best way to do business intelligence. So I got to have both. So over time, the data warehouse evolved, so it became distributed. So now you can cheaply scale it, just like you can a Hadoop cluster, a data lake, things like that. In fact, some of them work sitting on a Hadoop cluster or on the cloud, just like any other analytics capability. It still uses SQL as its primary way to do things, which means it uses all those BI tools. So your Tableau, your Qlik, your Looker, your Power BI, all those things still work. And you can still throw in SQL to do ad hoc queries. It can still do dashboards that you can give to 1,000 people. So it's got all the strengths that it had before, but it's sort of defeated that whole scaling issue that it had before. Plus, it's gotten way better at stream data, at accepting streaming data. A lot of them read directly now from Kafka or Kinesis or something like that. I work at Vertica, so all the examples I show you will be Vertica examples, but as much as I'd like it, if my competitors were asleep for the last 10 years, they also have these capabilities. So this is not just us. But that's the thing, is like, okay, this has become very sophisticated. It's defeated a lot of its old weaknesses, but we still need that data lake. Why? Well, we're still trying to dump a whole lot of raw data in. And as the database storage format is still, it's become more columnar as opposed to row, but it's still very structured and designed for high-speed querying. I mean, that performance is the one thing that it's just not giving up. Okay, so that's cool. So now I can dump my raw data. I can do my refining, my ETL. Now I'm doing it, instead of doing ETL, where I'm doing extract, transform, and then load, I'm extracting and loading, and then I'm doing my transformation on the data lake. Okay, and then I'm refining that. I'm doing data prep or ETL or whatever you want to call it, and I'm putting historical data, older data, I'm putting it in something like Parquet that's efficient for long-term storage. And the stuff that I want to query really quickly, like right now, I'm putting that in my data warehouse because we have that high speed performance. And I have to refine it a little more because their storage format is a little more refined. But I can throw my stream data in immediately and get an immediate response, and that's pretty cool. Wouldn't it be nice if I could do data science really high speed in that? But in the meantime, I can import and export Parquet. I can query Parquet because a lot of databases are now essentially query engines. And I can use my R and my Python and my Jupyter on this more refined data. Of course, I still have to pull out a sample and go somewhere else and do it and then come back and put it into production. But, you know, it's a pretty good system. The problem is it's so complicated. So yes, now I have the strengths of the data warehouse and the data lake, but it is crazy complicated. If I thought a data lake by itself was hard to manage, this is that much harder because I added even more complexity to my architecture. And we still have BI doing their work over here and data science doing their work over here. And in fact, data science is half the time taking a sample of the data and going off and doing their work somewhere else. They're not even on this system. All of these systems are defined and focused on where did I put my data? Do I store it here? Do I store it there? The person doing the analytics really just doesn't care that much where you put your data. So it's really about how you do your analytics. So let's look at an example of this combination architecture. So Uber's a good example of somebody who started out with a data warehouse and they evolved because they thought, well, I'll get a data lake. I got all this data. I don't need my data warehouse anymore. And they discovered rapidly that they were wrong. They needed both. They, in fact, discovered as their database was evolving over time, it added in a lot of those machine learning capabilities and things like that. And it had geospatial capabilities that were better than the data lake. So it's like, okay, well, I got to do my geospatial analytics in here. And I'm going to do some experimentation on the data lake. And oh gosh, you know, I really need to isolate some workloads because I have a data science and I have queries and I have all this stuff going at my database. So maybe I need more than one database and I'm duplicated and then I can pass it to, and the level of complication is pretty high. And, you know, they're Uber. They're smart. They can do this. So they wrote a bunch of code to figure out where to send their queries and things like that. And they did something pretty cool. Since they have a lot of Python programmers, and in fact, the Uber app is written in Python, but they wanted to connect that Python directly to their Vertica database, they created Vertica Python, Vertica-Python. It's on GitHub and PyPy and places like that. And they open sourced it, obviously. And now you could use Python and you could build Python applications and they could use your data warehouse. That's kind of cool. All right. So we're getting somewhere. That's starting to bring it together. And then you have like Simplify. Simplify isn't huge like Uber. They don't have 100 petabytes of data or a gigantic team. So they're doing all their stuff on the web, and they're trying to do it all on the cloud. But their need is they have to have it fast. Oh my gosh, fast. Very, very, very fast. So sub-second responses. So they are building their patterns and learning and everything. They're loading everything on the data lake and they're just using it pretty much to refine data and throw it immediately into their data warehouse. And they're putting all their real-time data there. Now their machine learning goes, oh, I gotta, you know, they're ad targeting. So they've got to respond less than a second. And that is their bread and butter. And that works. You know, they throw everything into their data warehouse, they get that fast response, boom, done. but they also need business intelligence, like everybody does. So what do? Well, they don't want to bog down their system doing business intelligence on what is essentially now their operational system. It's the system that keeps their business running, that does the thing that pays their bills. So they can't throw analytics at it because that might use up resources and slow it down. We can't have that. So they create another one, and they aggregate it down, and they structure it nicely for analytics. And this is kind of like a weird sort of ETL kind of thing, except that they're using the data lake to do their ETL, and they're using the data warehouse almost like a data lake. So it's like the lines are getting blurred. But now they have business intelligence, and they even did another one for executive dashboards. And none of this interferes with their ability to have sub-second response for their bread and butter. So that's pretty powerful and cool, and they've isolated their workloads. But what I've seen over time is these things are evolving closer and closer together. So the data warehouse and the data lake, the lines between them are blurring to the point where you can't tell where there is no line. So I'm calling this a unified analytics warehouse. I've heard it called a data lake house, a unified analytics platform, a unified data analytics platform. I've heard it called a lot of things. My personal preference is unified analytics warehouse, but your mileage may vary. But what this is essentially you take the extract and load, throw everything into something that resembles a data lake. And now it is essentially just mass storage. And it can be HDFS, S3, Google Cloud, whatever it is you like. And then you do your ETL on there. You do your data prep, you refine your data to something like Parquet. And now the thing is, in some cases, you also continue refining to your database format. It's all stored in the same place. It's all going to be stored on a cluster or on a cloud in S3, in HDFS, wherever you want to store that. But all three, raw, refined, and very refined, all those sort of stages of the data and the refinement that goes in the process, those are all stored in the same place. And on top of that, you essentially spin up clusters of your data warehouse. Now, this is mostly on the cloud, but I have seen this done on premises as well. So it's not just a cloud thing, but I think it started on the cloud and it has taken off and gone everywhere else. But the idea is I can spin up a cluster and it can cache some data from this storage to do machine learning. Or it can cache some data to do ad hoc queries, or it can cache some data to work for this department or that department. And the isolation of the workloads means we never bump into each other. So each department can do its own thing. And the data warehouses over time have developed more and more machine learning capabilities built into them, including the ability to let you train your data somewhere, your model somewhere else, import a PMML. It can import a TensorFlow frozen graph. It can do all these things that you kind of think of, manage your models like it manages tables. You tend to think of this as something you can only do in the data lake, but the functionality has merged until they are really virtually indistinguishable. And the cool thing about this is it's available wherever you want it. So you can have it on the cloud. You can have whatever cloud you want, Hadoop, on-premise, whatever. And here's the cool thing. The analytics is unified. You no longer have to take a sample and go do your R, your Python somewhere else. You can just stay right there. And interfaces like VerticaPy and VerticaPython and that sort of thing let you, and distributed R, let you do your capabilities right there. And there's a bunch of machine learning algorithms and data prep functions and things like that built in. And you can still do everything with SQL too. So you didn't lose your business intelligence capabilities. You just added on the data science. Now, if you talk to a data lake person, they're trying to do it the other way. But I think we had a head start on them because those analytics warehouses have been around for a lot longer than the data lakes. So that's it. You just unified your analytics. You're bringing your business intelligence and your data science together. And if you want to take your Jupyter notebook and work with your database that way and do, pandas or scikit-learn type functionality inside your database, totally can do that. That's pretty cool stuff. So here's a couple of examples. This is United Group. They pull everything in. Now the only difference between this looks a lot like a data warehouse architecture, except they're doing their transformation inside the database. They completely skip the data lake, unless you count the data storage which since they're on the cloud, is an S3 storage. And then they're streaming in Kafka and they're doing real-time ad targeting on TV, which is, I think they're the only ones I know of that are doing that. And they're also doing their business intelligence and their ad hoc queries and things like that. And because they're doing customer profile analysis, customer lifetime value, that kind of thing, when someone calls for support, they know their customer. And that makes all of their systems work better. So that's pretty powerful. Now, this is really more like what I think of as a unified analytics warehouse. This is the trade desk, and they stream everything into Amazon S3. They do a little bit of refinement on the Amazon into Parquet and things like that. They use Spark. And then they do one solid cluster that they have spun up, and they pretty much keep that. They have about 15 petabytes, and that subcluster is about 320 nodes. And that does most of their work. It does their BI and their machine learning and their ingestion and things like that. The thing is, they have to have 5,000 reports. Their business intelligence reports run their business, and they generate 5,000 every day. So what they do is they spin up 2 more 320 node clusters. That's pretty powerful. And they do some Python inside the database to do their machine learning, to do their real-time work. So this is pretty amazing stuff. And the one thing I want you to take away from this is not so much that the Unified Analytics Warehouse is the wave of the future, which I kind of think it is, but it is also the wave of the future right now. And 5 years from now, who knows? So keep in mind that things change, and don't lock yourself in. Be sure and keep your options open. Make sure that you don't decide that you can only use open source or only proprietary, that you can only use on the cloud, not on-prem, or you can only use this cloud, but not that cloud, or you can only, it's like, don't say, this is the only thing I can do, because going forward, that might really limit you, and things change really fast. So Unified Analytics Warehouse, EMA, kind of came up with this term, and they're doing a radar report for it now. But this is out now, and feel free to have a look. And if you'd like to try any of this out, feel free to go to academyvertica.com and try out our free training, certification, things like that. Or if you just want to try the software, our community edition is free for up to 3 nodes and up to a terabyte of data. And it has no expiration date, and you can keep it forever. So knock yourself out. Oh, and it has the machine learning capabilities built in. That's what my brain was trying to come up with. So thank you guys for coming. And if you have any questions, ask me in the chat, or I will be around the event. So give me a shot. Bye.